Yeah, my name is Karsten Beckhaus, come from Bauer. We do a lot of deep foundations, and I was allowed to make the link due to concrete for the geotechnical works for deep foundations. And these are the norms, the European norms I want to refer to, which is, first of all, the top section is what I call the geotechnical works, the design and then the execution, where of course there's a very strong link between. And for many of these geotechnical works, we need concrete, and if it's reinforced concrete, for example, we also need the the structural code for concrete structures. And that all together makes it the special geotechnical works, which is a better word for me than deep foundations. Anyhow, we often use the word deep foundations, and that's a link from the industry, from the European Federation of Foundation Contractors. We established a guideline making kind of a bracket of all these codes, from the design over the execution and with the concrete, with this, as you can read by the topic, concrete for deep foundations. The link is the concrete in the end, because these kind of deep foundations or retaining walls we have to fill with concrete to make it functionable, reinforced concrete structure. Yeah, so that's more or less the red line I want to use. This is what you design and what we execute, if it's not perfect, let's say. And these imperfections had been the reason more than 10 years back to introduce a group of experts from consultants and from the industry to work on this TREMI guide, we call it in short TREMI guide, bringing all the aspects together from the design over concrete to execution. So what we want to avoid is these very bad inclusions where any material is trapped into the permanent works. The middle one more or less addressing the lack of enough reinforcement, cover, or not enough clear space for the concrete to flow through, or bleed channels, which is often caused a minor issue, but anyhow, it's obviously an imperfection to these works. And if it's bad, then it's at the right, and I like to use this example from a study in the Netherlands, which the title was Bentonite Inclusions, where you can see how that someone already made some pre-assumption what is the reason for this faulty or defective diaphragm wall panel. And in fact, it's a complexity in the end. So it's you see in the middle, or you can at least assume there is overlapping bars. So the reinforcement have just a little space for the concrete to flow through. So it's a splice section. It can be the bentonite, can be working procedure, or just a bad or poor quality of concrete. In the end, I would say it's not the perfect teamwork which led to this bad example of geotechnical works with a defect. This is just going a bit back because we try to find out what happened to the concrete in over 50 years. And let's say 50 years back, when the concrete was what we call a three-component type of material, just aggregates, cement, and water, life was quite simple. And we had a principle of good workability at a sufficient stability, which means no segregation of gravel, etc. in the concrete. And then we had this application rule in the end. With a new concrete, or new generation of concrete is already many, many decades old, we got additions and admixtures as well. So you had a lot of ideas to compensate to your concrete. And at that time, when the standards were just not developed further, just copied and used again, we ignored this principle of good workability at sufficient stability, because the material is not the same anymore from its rheology. But we still use the same application rule, consistent and for slump and spread. That's the only one, let's say, measure we can take, or we took at the site. And that was the starting point, is that we have to change this one. And we started the group, that's very short. We started the group in 2014. We had a very large, extensive research program with 2 universities in the US and in Europe. And then we brought out a second edition of this TREMI guide, having all this information included, and proposing new acceptance criteria, new way to design concrete, and to really rate the quality of concrete by a performance-based concept. Yeah, if you want to see more of these, you're invited to Brussels, to Bruges in Belgium next year in May, where there's this EFFC conference where you can see more examples of, let's say, practical applications. So this new third edition of the TREMI guide is coming out this month. Is it still October? Okay, so in November, and it has still the same agenda. You see it with the list here, the table of contents, that it connects all these aspects of design, and design more or less just, let's say, reduced to cage detailing. I come to this in a minute, but also then specifying and testing of concrete. We have many execution examples and recommendations in there, but we also talk about full-scale trials. Again, the connection to EC7 and quality control of completed works, also of non-destructive testing. And section 9 is still evolving chapter on numerical modeling of concrete flow, because we can learn a lot from numerical modeling, much easier than to do full-scale trials in the end to learn. So this is the actual topic we are talking about. The revision of the EN 1536, that's the execution norm for board piles, and 1538 for diaphragm walls is active right now. So the revision is ongoing in Working Group 25. There's also another working group by the TC 288 for micropiles and for diaphragm walls, and more are active, but these are just the ones on piles, more or less deep foundations. In this graph, you can see that all these norms are connected with just when we go through the, let's say, course of getting the right concrete for a certain job site. We start, of course, with the design, then we go to the structural design in any case, and then we need the constructor with the concrete experience and the knowledge to balance the concrete in the right way. And in the end, you have to order something at the supplier, and then we come to the execution and just have to fill the concrete in the borehole or into the trench. This will probably also be in the new EN 1536 and 1538. 1538 then with a rectangular picture. But this is what we recommend and what we have learned, and where we also see a conflict with the EC2. Anyhow, this is learned practice, where we say on the left side, you see, we need a certain cover, not for durability in the end, just for execution. If we just see the concrete has to flow through the reinforcement and to embed the steel, we need a certain nominal value for cover. And we use the same terminology, of course, as the Eurocode. And in the former version of the execution standards, there was a bit of a misunderstanding, I would say. C-nom, C-min was a bit controversial, I would say. But we will clean it up, and in this TREMI guide it's already made with the same thing. So if you want to go for a nominal concrete cover, you have two reasons, and that should be, let's say, you should choose the value from structural reasons or executional reasons. But the maximum value is, of course, the one you have to apply in your cage detailing. Come to this later. Should be 75 millimeters at least, the C-norm. The spacing itself is much wider than the structural works the EC2 guys usually know, because we need to have the concrete flow by itself, just by the weight of the concrete head on top, through the reinforcement, as you saw with the picture before, that it might be hard to flow through a very tight opening. That's why we have this absolute minimum value of 4 times aggregate size, but there's also, so depending on the aggregate in the concrete, but also a minimum value, which is usually 100 millimeters for deep foundations, so at least a space of 100 millimeters to get the concrete through. And on the very right side, the same as always, you need to have some play for the reinforcement cage to fit into the excavation. Yeah, as I said, partly conflicting with the EC2, I'll come to this in a second. So this is the EC2. just in the section 6 on durability and concrete cover, you see, I just put it here, 12 pages just on this topic, which is, if you read through, it's fair, because there's a lot of things to consider. But the part I will concentrate on is here in 6.5, concrete cover. Again, as we have pointed out in the TREMI guide, there's two reasons for concrete cover. One is for durability in the end, so when you have your final product, and the other one is just to get the concrete there where you need it. That's for execution reasons, which shall be covered also in the future by EN 1536 and 1538 for piles and D-walls. I think it's sure it's correct to have this C-nom, it's equal to C-min, minimum cover plus an allowance for deviation. That's standard practice for years, for decades, no question. And the second line is also fine. The minimum cover itself is already a maximum of several values. It's either for durability, which is normally the decisive case for us, for bond, or at least 10 millimeters. That's the absolute minimum. With the durability, you see there's also the sum of additional delta C's, which you shall take into consideration. For example, there's also a possibility for deep foundations maybe to reduce the minimum value for durability, but probably seldom used, but let's see where we go. So you can use, if you have a shorter design life than 50 years, for example, or 30 years, I think it is, and if you have a very good curing, which we always have in deep foundations. So why not using it? Sometimes we use it, but also in, only in cases when we need an excuse. Minimum cover for durability, it says the minimum cover, concrete cover, covers C&U depending on design service life. Exposure, the class and exposure resistance class are given in table 6.3, and this is an NDP. But of course, it's a EC2 working groups looking into these NDPs, not us. Come to this in a moment, because I would have at least, if you are in one of these national groups, maybe you have a reason. So with the allowance in design for deviation cover, I see a conflict with our daily practice and with our experience from 50 years and more. So again, it's no question that we have to add something to minimum cover. This is where it refers to this table 6.7, just for this deviation in cover. There's a note, so first of all, it's a shell. No question that we have to take it into account, and it has to be specified in the execution. It has to be specified in the execution specifications. So that's the value you need to respect in the end. Values are given in table 6.7, and this is an NDP, which means we can change the 6.7, not me, but the national annexes. In line 9, and this is a dispute in the end, concrete cast directly against unprepared soil should have an extra allowance of 75 millimeters. And I put this index A here. These allowances for different deviation also apply for board piles and for diaphragm walls designed according to this Eurocode. So in the end, we have to apply. There's no way out except we change the 75 millimeters to another value, which I would propose. So even for a, let's say, relatively low or normal minimum value of 30 millimeters, which is already 25 plus 5 millimeters for another reason, plus 75, we would have something like a standard case for 105 millimeter of nominal cover for a standard board pile. And that's what I mean with a conflict I'd like to address here. So this is just a few slides, which is probably not in this dispute at all. So the definitions are fine, everything is good. That we need for board piles and diaphragm wall nominal cover, values for durability, etc., is clear, and the Eurocode makes clear that there might be other values in EN 1536 and 1538 for execution. All good, that's no debate here. But it starts with the value for C-min, with this small sum of delta C, where we have another 5 millimeters for the reason So it's also note the increase of the cover, just of the minimum cover, not talking about the allowance for deviation. Another 5 millimeter for casting against a vertical soil surface has to do with the observation of a, let's say, not perfect concrete in the cover zone, giving a reason of giving some more sacrificial layer. But the 5 millimeters, I would say, we have to the outer side anyway. So we were from France and from Germany, we were applying comments to these codes, but there would have been just put it in a note, and still you can change this value into in a national annex to 0. I would recommend, because we have a good reason for sorting out the cover, the necessary cover, in the execution standards, not in the design code. Again, so this is where you get these from these tables, the numbers for durability, 25 millimeters for this one example. You have to add this 5 millimeters sacrificial cover, and then you end up with these 30 millimeters plus 75, as I showed before. You would end up with 105 millimeters. So again, then you might start with reducing by 5 millimeters here and there for any allowances in the code, but in the end you will end up in a region of 100 millimeters standard cover. This is a famous table 6.7 with a line 9 concrete cast directly against unprepared soil. In the former code it was already unprepared soil, but we always said when we drill or bore, the soil is not unprepared anymore. We prepare it for filling concrete in, which is a bit of a weak argument, but with this footnote A, that's gone. Okay, coming back to the execution, that's what we have as a, let's say, proposal, because the guide is only a recommendation, but we will have the same in the EN 1536 and 1538 in future, that we clarify we have a minimum cover and a nominal, and a deviation, and with 50 millimeters as a minimum cover, just to allow the concrete to flow through the reinforcement and to embed it. We are usually above the values from EC2. Plus 25 for allowance, which gives us a normal case from a practical reason for 75 millimeter of nominal cover, which is still, let's say, a good value. So Simin Exer, and that's, we use the index Exer for execution here. The EN 1536 and 1538, as said, under revision right now. I'm the convener. We are more or less in the middle of that work. We have some major amendments, I think, which will be obvious in the end. So we make it quite shorter in the end. So we have deleted already lots of textbook phrases. We are updating the whole guide, the whole norm. For example, with this C-min and C-norm. We have sorted out some conflicts, I think, with where the EN 1536 and 1538 took a bit too much notice of designing things, so we sorted it out. So we reduced the number of, let's say, design considerations and tried even to streamline them into the relevant section. So I think there's no conflict anymore with EC7 and execution standards. Yeah, but we have to solve the issue with EC2 if we can in our execution standard. So at least we will try. The barrettes, maybe some of you know that the barrettes had been in the piling standard before. They go back into the diaphragm wall execution standard, where they belong to, I would say, just from the execution point of view. We are harmonizing with the EN 14199 cast in situ, sorry, micropiles. Sorry, Klaus. Micropiles, not cast in situ micropiles, and displacement piles. We request geotechnical description of ground properties regarding their drillability. That's new, I think, because it's not only design, we also have to plan our works and to price our works. So that's why we have this drillability or excavation ability also as a task in the execution norm. We are incorporating normal requirements for polymer-based slurries, not only for bentonite slurries, so we really put them on the same level. And we will introduce probably a table on water tightness of walls, because it's always very often a dispute what is watertight in the end. So we try to make a clear link to the execution standards as well. So that's just a few just examples from where we are. in this specific information, geotechnical information, that's what I said, to drillability, ground properties necessary to determine work method, equipment and tools, and to estimate performance as well as wear and tear. For example, regarding strength, density, abrasivity. This is given as one example for relevant information which should be given to the contractors. Materials and products, just to say, yes, the support fluids, there's one chapter, bentonite, support fluid, doesn't matter. So you can have also tables where we are still let's say, discussing the values in the end, which you will have then for acceptance. But there will be two tables, but at least one for bentonite, one for polymer, maybe a second one for different kind of polymer-based material, because it's also very extensive. And this is completely under progress. The work how we define the water tightness of walls should be equivalent more or less for D walls, for board pile walls, of course, different, what you can achieve, but at least the depth of requirements should be parallel in both standards. And again, I don't go back into detail here. So we will focus on the let's say on the cover and spacing of rebars necessary to install piles and D-walls of high quality. And again, we have to live with this NDP probably. That is probably to be solved in each standard body. Coming back to concrete very shortly, just to make sure, to show that we also go into details what the rheology of the concrete is, to understand the concrete in this context of geotechnical works, and what is in the center of this table, what is properties, characteristics we can really control, we can check, we have tests for that, because rheology is not very complicated, but you can't have a rheometer on site everywhere, so we need to get back to simple questions and to simplify the material by its performance. And the blue line showing tremi-concrete, it's not a concrete you usually vibrate, it's not a concrete which is a self-compacting concrete, so we need expert test methods for that. And of course, for the concrete supplier, it means we need to have another concrete mix design where it goes back this line. What is the control possibilities of concrete we have? What is the impact of different additions? But that's all sorted by the concrete specifier and the concrete supplier in the end. He has to understand, but we have to give performance values how we want to define the concrete so that it really is workable enough. And this is more or less the final recommendation for the slump flow value, which is a very simple test, the same as you know. You just not measure the slump anymore, but the slump flow, because that's more sensitive. And then you go into a range of target values, and then you can have also identification on site. Yes, that's the concrete I designed, because in the evolution of the concrete design, you can do more tests. But on site, you want to have it simple, one test. We call it a triple test, because you not only have the slump flow, you also can see how fast it is and how sensitive or prone to segregation it is. Yeah, expert tests are necessary for our types of works, because often we have very long pouring times, which is specific, different from other types of concrete works. That's why we usually need some admixtures extending the workability lifetime of the concrete, and also we need tests for that. This is all under the scope of the tremi guide. And that's all to avoid having stiff concrete already in the excavation on the right side, and then having a fresh concrete trying to escape somehow, and then we call it volcano effect. And that's what we think is the reason for these inclusions. I showed you one of the very first photographs. That's how it should look like, a bulging flow. That's what we expect to have in a reinforced concrete element anyway. And then we have this very simple recommendation or requirement. Please do this test. This is your target value. Test it on site, and then everything should work, or you have to reject the concrete, of course. Very shortly, all these, let's say, findings and work done in the last 10 years in the, with these concrete task group in the EFFC have been used to revise the EN 206. It was formerly the Annex D for concrete for geotechnical works. It will be in future a new Part 3. just on additional requirements for specification on conformity of concrete for special geotechnical works, which is kind of I put it in as an upgrade, because it was an appendix or annex before, normative of course, but now it's a known part. And the same rules apply as before. For tremi-concrete we have extra rules, as I described before. And we have, of course, merged and simplified a little bit the wording, because before we had rules for diaphragm wall concrete and rules for board pipe concrete, which is the same type of concrete, so we put it together in one tremi-concrete in the end. This is some of terms of definitions you will find in the new PM02 Part 3 for concrete, for geotechnical works. So words like workability have not been in the EN206 in the mother part, for what reason, I don't know. Stability, workability, retention, that's the reason for this long workability of concrete. So we have introduced new terms we need for specifying concrete for geotechnical works. In the middle part, you see this 450 millimeter of slump flow as a recommendation for a new acceptance criteria for concrete workability. And what is also new is the requirements on plastic concrete. So concrete for cut-off walls, not only for structural walls. So that's your 1 to 2 megapascal material you will find also in the EN206 Part 3. Coming to the end, just a few words on what is the concrete flow mechanisms inside, let's say, in this kind of a pile. As I said before, on the very left side, that's what we expect for a bulging flow, what we call in a reinforced concrete element. But to the right side, the plug flow is probably the name. When you don't have any restriction to flow on the side, you just heave the concrete, the first load of concrete, to the very top, and you will find on the very top, even after 50 meters, you can still find the first batch of concrete on the top, which is not the case for the left side. But that's very, very clear. It's not either or. Something in between can happen as well. It depends on the width of the panel, or pile, and the height as well, etc. There's also a chapter which is linked to EC7. So it was, let's say, on the wish list of our consultants in the team to have really focus also on the opportunity to make full-scale trials for large jobs. We have one in Scotland right now where this picture is from, which it makes sense. If you are close to the edges or to the borders of a standard, of a norm, then really try it out and show that it's workable, and then keep to the work methods you have then verified with this full-scale trial. Quality control of completed works. We have dealt with let's say, the typical types of non-destructive testing in an annex. We will have, in the industry, we have decided to have an own guide to non-destructive testing methods for all these geotechnical works, let's say for deep foundations, cast in situ. This is probably due maybe established in another 2 years, but also the traffic guide already has some recommendations on how to apply and where to stop, at least with the assessment of imperfections. And last but not least, it's very, very ongoing, the work with the numerical modeling. So when we started 10 years ago, we haven't had the numerical modeling of concrete flow at all on our list. With the second edition, yes, we started already to learn a little bit from numerical modeling. Within the last 5 years, the evolution has been enormous. And today we're looking back to a PhD thesis done in the UK, which is very close. So Arab was also accompanying this work, and we can not only learn because we know somehow how the concrete flows. That's what we said, this plug flow. You can see that with these streamlines how it works. When there's restriction to flow through the reinforcement cages, it looks different. So first of all, you can simulate what we know already, but then you can learn by sensitivity studies. You can learn what is sensitive to concrete flow in the end, and very detailed measures, numerical modulations have been done. And on this, let's say it's a very short movie, you can see that the concrete, I probably have to go here, because it at least looks quite nice.
It doesn't work, sorry.
Doesn't work?
It doesn't work, video not
disponible. No video. You would see that the concrete flows exactly like I said before. So it goes sideways through the reinforcement. It will never really go up to the reinforcement, and that's what was proven by the numerical modeling and by several full-scale trials as well with dyed concrete, etc. So you can learn from these detailed views here what is the data height inside, outside of the reinforcement. It gives you something of the quality of this complex situation, reinforcement with concrete. And if you have a support fluid in the cover zone, of course you also have something which you have to really displace here. That's it. This is maybe the short commercial break. If you want to support the further numerical work done in the UK, you can get back to me and pay 5,000 euros, and you get a sponsor logo in the training guide. Or you're just interested, and then we can share the information here. So in the end, it's very simple, I think. Special geotechnical works made with concrete need geotechnical design according to EC7. We needed EC2 respected, and also the requirements for execution. That's, yeah, I've told about my conflict with the 75 millimeters. Performance-based concrete at high quality. Execution compliant with EN 1536, 1538 for the deep foundations. We also have state-of-the-art recommendations. The trend guide is one example, I think very widespread over Europe and the US. But in the end, it's good teamwork we need, and that's what I think is also the idea of this meeting here. Thank you so much.